So we kept doing public encryption for, how many lectures was it? 3, 4 lectures. So we're done. We're going to move on to something even more interesting, which is really zero knowledge interactive proofs. But to get there, we have to sort of set things up. I have to tell you what we are solving, set up some tools. Okay, so really, one big difference between whatever we did in the last, so many lectures, 10, 11, 12 lectures, and today, the next 2 classes, is the question of who is the adversary. Right? So, this is a question that we constantly ask in cryptography. So far, our goal was secure communication. Right? So I sent a message to you. Either we had a shared secret key or we didn't. Right? Secret key or public encryption. But in any case, the adversary was someone who lived on the wire, essentially. He was an eavesdropper. He could see the communications between the two of us, and he tried to figure out what was going on. The adversary lived on the wire. That's the point. Today, the adversary won't live on the wire. He won't just live on the wire. The adversary will be among us. Right? The adversary will be you, maybe, me, maybe, right? So the point is that if we move beyond public encryption, we want to have more complicated protocols, interactions, where the adversary is, it could be one of the protocol participants. For example, think about, auctions, right? Auctions happen all the time. Now, much more than ever, ad auctions, for example, right? So there are parties here bidding on the value of an item, and then there's an auctioneer, right? So there is a protocol sort of happening between all of these parties, and each party has an incentive to deviate from the protocol, right? So the parties, the people who are bidding, have an incentive to, overbid or underbid. They have the incentive to look at the communication channel and see what the other people are bidding potentially, and change their bids depending on that. The auctioneer has an incentive to favor one bidder over the other, right? So this is one example, just one example of an interaction where there are many parties in the system, at least 2 parties in the system, right? And each party has an incentive to deviate from the protocol. And we want to sort of make sure, cryptographically, that all parties, there is a fixed protocol that all parties agree to, and cryptographically, we want to ensure that all parties behave as they are told, as they are sort of constrained by that. Right? So that's where zero knowledge comes in. Okay? So let's start from something really, really simple, and that is the setting of proofs. Right, proofs, is one mechanism to ensure that people behave according to certain sort of pattern of interactions. Proofs, we are going to think about them as, let's start from mathematical proofs. Okay, so what is a mathematical proof? There is a statement, right? There's a claim, there's a statement. For instance, I'll give you a number. Proofs have a claim, statement, or theorem. We'll use all these words interchangeably. For example, n equals is a product of 2 distinct primes. Yes? Doesn't have to be. It could be saying, here is a ciphertext, right? That could be the claim. So, example, C equals 1101110000111 is an encryption of 0 with respect to public key something using the Goldwasser-Mikhaili encryption. This is a statement, yes? Yeah, these are all statements. These are all theorems, statements, claims. And how does one, there are at least two entities in the world. Okay, there is a prover and there is a verifier. The prover is privileged somehow. The prover is privileged because he knows the proof, or he's computationally unbounded, so he can figure out the proof by just running forever. Okay, so the prover. So there are two entities in the world. There is the prover and the verifier. The prover is computationally unbounded. So he can figure out the truth or falsity of any statement. Right? Then there is a verifier, V, which is polynomial time. In fact, because everything we do is probabilistic, I'm going to say it's probabilistic polynomial time. That's the verifier. Then there's a claim. Okay, so this is a claim. I'll call this X. Yes. The verifier knows X, and the prover also knows X. The prover also knows, because he has unbounded computation, he knows whether X is a true statement or not. He knows whether this number is indeed a product of two distinct primes or not. He can figure it out. Just factor exhaustive search. Now the prover wants to convince the verifier that this is in fact the case. So how would you do that? I mean, traditionally, mathematics has dealt with proofs for centuries. So what is the canonical way of proving statements? How would the prover? Not a trick question. Too early in the morning for trick questions. How would the prover convince the verifier?
Send a transcript of the proof.
What does that mean? What does that mean, transcript of the proof? I mean, this particular statement, right? The fact that,
Well, you have to, one thing would be to provide like the two primes that multiply to it, but also probably have to do some proof that like those are prime as well. So like, I don't know, some computation of like is divided by every number less than it or something.
Okay, good. So let's deal with the situation where n is in fact a product of two primes. Okay. So then you're saying, look, the proof is in fact the two primes, p and q. Yes. So this is when n is in fact p times q. I provide p and q to the verifier. Yes. The verifier, what does the verifier do? I mean, given the proof, he checks two things. One, that n is in fact equal to p times q, right? Yeah, this is in fact a true statement. And two, that's not enough. Like you pointed out, you have to also check that p and q are themselves prime. And thankfully, primality test is something that can be done polynomial time. In fact, even deterministic polynomial time these days. So do check, V checks that P and Q are prime. Yes? Very good. That's it. So what we want is that if n is indeed a product of two distinct primes, the verifier would accept. So V checks if 1 and 2 pass, V accepts, otherwise it rejects. Yeah? That's it. So if n is indeed a product of two distinct primes, we will accept. P and Q are prime, P different from Q, I suppose, right? Yeah. If n is not a product of two primes, two distinct primes, there's nothing that P can do to make the verifier accept. Yeah, that's cool. You with me? Convinced? Yes. These three conditions together ensure that the claim is factual. Okay? So this is the notion of a proof. What is the notion of mathematical proof? There is a theorem statement. Yes. There is a sequence of axioms which we all believe. So the theorem is not a theorem unless you say in what system of axioms is this a theorem. Yes. So this is something that we all agree on. And the proof is a sequence of steps that takes the axioms, puts them together using sort of rules of inference to get more and more complicated things, eventually arriving at the answer. Yes. Right? So the soundness of the proof system guarantees that if there is a sequence of steps starting from the axioms and the rules of inference that leads to the claim that you have, then it is the theorem is in fact true in this system of in this proof system. And conversely, completeness says that every true theorem has a proof in this system. Okay, so this is mathematical proofs, and in fact, in computer science, so mathematical proofs don't talk about efficiency at all. So this doesn't matter, right? I mean, it's it just needs to be a sequence of steps. It could be an exponential in what? Exponential in the length of the theorem. You care about number of steps to prove a statement. Mathematics doesn't care. In computer science, we do care, and that leads us to the notion of NP proofs. And P is non-deterministic polynomial time, and here we will work with sort of decision problems. In other words, decision problem is unlike sort of factoring numbers where, well, actually, this is a decision problem. Yes, given n, is it a product of two distinct ranks or not? In general, a decision problem is defined by a subset of 0, 1 star, the set of all strings. These are the true theorems. Okay, so any subset of 0, 1 star is a language that defines a set of true claims. Such a language is defined to be an NP if there exists a polynomial time, no probabilistic at this point, so polynomial time verifier V such that the following two things hold. This is the case with any proof system, right? True theorems should be provable, no false theorems should be provable. These are the two properties. So we call them completeness, which says that for every x in the language, for every true theorem, there exists a witness W, this is a string W, not too long a string. Formally, I should say there exists a polynomial time verifier V and a polynomial function poly such that, so on and so forth, such that V on input X and W outputs accept 1, let's say. Yes, this is complete. There is a proof that the verifier accepts. Here the proof is P and Q. The statement is N, the proof is P and Q. To soundness says that for every x not in the language, yeah, complement of this, and for every witness W, for every potential witness W, so the strings outside the language don't have witnesses, by definition. For every string W, of length quality x, V of x W says reject. Okay, so this is sort of one way of sort of a definitional way of thinking about it, right? So every statement in the language has a proof. Now, this definition doesn't say how to find the proof. Right? It just says there exists a proof of length polynomial. And soundness says that take any string not in the language, there is no proof. No matter how you try to find it, there is no proof that can make the verifier accept. So in this, the semantic, the operational way to interpret the NP definition is that there is a game happening between a prover and a verifier, an unbounded prover and a polynomial time verifier, no probabilistic. Okay? Where the prover can send a string to the verifier. The string happens to be the witness. How does he find the string? Doesn't matter. He's computationally unbounded, so enumerate over all possible strings. Right? And the verifier gets the x and the witness W and decides to accept or reject, and this says the right things. And true theorems will be accepted, there is a prover that can make the verifier accept from truth theorems. And no matter what the prover is, you won't be able to make the verifier accept for false statement. That's the. Okay. So again, the prover verifier way of writing this is the following. For every x and L, they should define notations. Okay. So P and B, this notation means the interaction between P and B. Here there is not much interaction. P sends a message to B. That's it, right? This is P and B. This denotes the transcript of the interaction. Output. This means give Px, Vx, both of them the same input. What is the output of V on this interaction? Okay? So this is by definition here either accept or reject, either 0 or 1. So NP says the following. There is a verifier, it's a polynomial time verifier V such that 1 for every x in L, polynomial time verifier, and the prover unbounded potentially prover P such that for every x in L, out sub V equals 1, so, and for every x not in L, and for every P star, yes, so the verifier is the verifier that we define. What is the prover? The prover is the guy who takes the n, right? He decides if n is a product of two distinct primes. If it is, he finds those primes and sends it over to the verifier. If it is not a product, if it's not in the line, the string is not in the line, and it's not a product of two distinct primes, he says, well, look, it's not. Yes, that's the prover. That's P. What I want is that for every P star who does anything different from what P is supposed to do, they still cannot make the verifier. P star x is reject. Yes, doesn't matter what soundness is with respect to a malicious prover that tries to sort of prove a false statement. And this number 2 says that no such prover can possibly succeed, even if they're computationally unbounded. Yes, but yeah. Which one wants to go first? This is a deadlock. Okay, let me. Yeah.
Wait, what are the malicious provers like except?
What if he outputs accept?
Yeah.
The prover can do whatever they want, but the verifier expects something from the prover.
Oh,
yes.
malicious provers.
Right. So the malicious prover can just say, look, trust me, this is a product of two primes. The verifier will say, that's not. Right. Good. So what you point out is an important thing, which is soundness is a property of the verifier. Right. You can design bad verifiers, like stupid verifiers, who say, I'll do whatever you tell me to do. That's not a sound proof system. So soundness is inherently a property of the verifier. Good point. Yeah. Yes.
And just to confirm, the verifier that you chose for the first condition is the same verifier that you're trying with the second condition overall.
Correct. The same verifier. So the language, the NP language, comes with a PNP. And the first condition says, in the normal mode of operation, when nothing goes wrong, things work as expected. Okay, that's completeness. Soundness says when one of the parties tries to cheat, P star, he cannot cheat the yes.
How hard can computationally unbounded be? Like, is it?
Say again.
How large can, how much computation can be done when you say unbounded?
Unbounded computation. But I don't assume anything about the computational power.
So every decision problem is NP?
No. 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 So NP requires that there is a string of length, polynomial in the length of the statement that I can convey to you. That'll make you either accept or reject, right? For instance, what is it? Good. Here is a problem. I give you a configuration of the board in chess. The question is there a strategy for the white to win no matter what the black player does? How would I convince you of the statement, right? So the statement is a board, it's a configuration of the board, and the claim is that for every strategy of black, there is a strategy of white, which makes the white win. How would I convince you of this? It's not clear how long the game runs, first of all, right? I could try to give you a transcript, but then what would the transcript be? A move of white, a good move of white. But then I have to quantify over all possible moves of black and say, well, for each of these things, I have a winning strategy. So I'm lost. Even if the game only runs for polynomial number of steps, I'm lost already. Right? So this is an example of a problem in P-space. It's in fact P-space complete, appropriately defined. And we believe that P-space is not contained in NP. In particular, this problem doesn't have a succinct witness. So, yeah, yes.
Well, but every problem will have the P, right? But not necessarily not P.
Every problem has a P which produces potentially very long transcripts. So here you can produce it. There is a P that produces a transcript, right? Enumerate over all possible strategies of black at every point of time, right? It's a finite game, so. But yes, but a problem is an NP only if there is a verifier. There's a polynomial time verifier that checks things. That's it, right? Yeah. So the key character in an NP statement is the verifier. The prover is kind of trivial in a sense. The prover is something that exhaustive searches, since they are computationally unbounded, they can exhaustive search over the space and try to find a witness. The verifier is the important entity. Okay. So this is NP proof system. Just to sort of calibrate myself, how many of you have seen the definition of NP in previous classes? Many. Okay. So this must be familiar to you. Right? Which classes actually? 045, raise your hand. 046, raise your hand. Okay, all right. This is before they destroyed 046. No. All right. Okay. Good. So this is a proof. Now let's think about it. So we already protected against the malicious prover, right? That's what soundness does. But let's turn the tables and look at the verifier. Okay. Because cryptography, you don't know I'm bad, and I don't know you're bad. Yes, everyone is potentially bad. The prover's goal is, soundness is to convince the verifier of the truth of a false claim. What does the verifier do here? The verifier is, poor thing, is polynomial time. Okay, so it doesn't seem like he can do very much. But he looks at it, he looks at this interaction, he sees what's coming through, right? And he could learn things. He could learn sort of new things from this interaction about the statement and about the witness potentially that he shouldn't, ideally. Okay. So in this interaction, what does the verifier learn? I mean, here, for example. Right? The verifier learns number one, okay, that n is a product of two distinct primes. He learns the truth of the statement, but he's supposed to learn it, right? I mean, that's the whole point of the protocol. He is to convince the verifier of the truth of a statement. So he learns, the fact that he learns the truth of the statement, no problem. Two, he learns more than that. He learns the factors of n. Yes. This is more than the truth of a statement, right? This is actually the proof of the statement. So typically in mathematical proofs, in NP proofs for that matter, the truth of a statement and the proof of a statement are inherently kind of tied together. Yes, one reveals the other, yeah, they seem to go hand in hand. Really, the work of Goldwasser, Mihaly, and Rakov, they challenged this assumption. Yes, so do they have to go hand in hand? Can you separate? Can you come up with a way to prove things where a prover can convince the verifier of the truth of a statement without revealing the proof, the NP proof, the witness of a statement. That's the question. The answer happens to be yes, but we'll get there slowly. Okay. Good. So, good. So let's get there slowly. So to do this, they had to change the notion of a proof. The notion of a proof, like in NP, yes?
Is this true for any statement in NP?
Correct, yes. We won't show it today, we'll show it tomorrow, the day after, okay? So every statement in NP can be proved in zero knowledge. It's a fantastic theorem. In fact, not even every statement in NP, but every statement in something called IP, which we'll define in a minute, which can be proved interactively, can also be proved in zero knowledge. So basically everything. Everything that is a proof has a zero knowledge proof. That's the bottom line. Okay. So, but slowly. Okay. It'll take me some time to get there. Good. So you need to change the notion of a proof, and you need to add two ingredients. One is two new ingredients, and both of them are necessary. Without either of them, there is no zero knowledge. Zero knowledge is unachievable. One of them is interaction, and B is randomness. It's interaction in the sense that we want actually a protocol between the prover and the verifier. We'll see in a minute. The prover talks, and the verifier talks back. The prover talks, the verifier talks back. Blah, blah, blah. Right? At the end, the verifier says, "Thank you very much, I'm done, I'm going to decide." And once he decides, we want completeness, and we want soundness, and we want zero knowledge, but we'll get there in that. I haven't even defined what that is. That's interaction. Randomness, because I want the verifier to toss coins, to be able to toss coins that the prover cannot see. Okay, so he says, toss coins, I send something to you. Yeah, that I want. Okay. So without both of them, there is no, you can see, right, without randomness, yes. Why interaction? Why do you need interaction? Because the prover sends a message to the verifier has no randomness, right? So whatever he does is a function, polynomial time function of both the message and the x, which the prover can compute it himself. And he says, well, you know what, let me run you in my head, here it is, and then keep going. Okay, so the interaction is useless without randomness. Yes. Randomness is actually a little bit useful without interaction, but that's a fine point. We won't, only marginally so. We won't get to that fine point. Well, parenthetical remark for those of you who know a bit more complexity theory, with only randomness, NP can be sort of upgraded to a complexity class called MA, which is a bit more powerful than NP, but not a whole lot more. Never mind, it's a parenthetical remark. Okay, so we need these two ingredients. Okay, so let's try. Let's try not with the language of two, product of two primes, but rather the quadratic reciprocity language. Okay, so let's define the language. L is the set of all n comma y, where y is a quadratic residue y. This is a quadratic reciprocity language. And a theorem, a claim, a statement is a pair n comma y, and I want to check if this is the truth of this statement. Yes. Good. A classical NP proof would be what? I give you a square root. If the theorem is indeed true, and y has a square root mod n, I give you the square root, and you check. Yes, very simple. I want a more interesting. So this is again, intuitively, not zero knowledge, because I'm actually giving you the square root of this number, yes? Something you could have computed yourself. So I am giving you knowledge. We'll define what that is in a minute, but intuitively, I'm doing something wrong here. I want to do something else, yes? What is another way of, you come up with another way of proving that y, you know n and y, I know n and y, I am computationally unbounded, yes? And we want to interact gets completeness and soundness. Forget about zero knowledge for the moment. Although you have to keep in mind, without that, I could have sent you the square root, yes? What is another way to prove this? Let me actually, you know what? Okay, so L is this, yes? L prime, let me define a related language. Y is not a quadratic residue Y, yes? So we'll call this the Q and R language and the QR language, yes? I mean, they are essentially complements of each other. So this guy, it's not even clear how to give you an NP proof. I mean, what do I tell you? Yes.
You could send a prime where it's not a quadratic residue, modulo that prime which divides n.
Good. Or I could send you the factorization, then you decide yourself. Yes. So I take back what I said. It is clear now that there is an NP proof for the statement. But again, I want a more interesting. Give me an interactive proof. And don't tell me the word part sends nothing and the prover sends the product of the part. Something more interesting than that. How would I? Think about the Goldwasser-Micali crypto system, which I don't know if you remember. Do you remember? Should remember. So there, the public key was a quadratic residue, yeah? And the encryption was of 0 was a random square. And the encryption of 1 was a random square times the y, the thing in the public key. Yes. So of course, if y is a quadratic non-residue, a decryptor can use a factorization to distinguish between the two. Yeah, that's why it's correctness. And then security and so on and so forth. But never mind security, just correctness, yes? Imagine for a moment that for whatever reason, okay, when I came up with the public key, I set y to be a quadratic residue. Why would I do that? It's completely unclear, yes? Because what happens if y is a quadratic residue? You are the guy that sort of looks at n and y, decides to encrypt 0 or 1. Let me write down the game here. The game is this. Public key is n and y is not in the quadratic residue. And this is Goldwasser-Micali. Right? So this is something that I picked, and I pick this together with P and Q and I keep it secret, yes? Who comes in and says, well, 0 or 1, she sends me an encryption of either 0 or 1, which happens to be r squared, a random square, times y to the power b. B is the bit. Right? So this is either a square if b is 0, or a non-square if b is 1. And I have the factorization, I can tell what is what, but an eavesdropper who looks at this channel, by the quadratic residuosity assumption, cannot tell what is what. Now imagine that I am, set y to be a quadratic residue. Okay. What happens? Okay, same encryption. The encryption algorithm is still the same. Pick out the y, then do r squared times y to the b. Can I decrypt? When b is 0, this guy is a random square, yes? And when b is 1, it's a random square times a fixed square, which is a random square, because the set of squares is a group. Yeah? So it doesn't matter that I have the factorization, I could have 42 for that, and I wouldn't be able to. Yeah, the question for 42, but I wouldn't be able to decrypt. No, nothing that I can. So this ciphertext completely hides the bit b. So I really shouldn't be doing that kind of thing, right? Because I'm shooting at my own foot, like, Yeah, if I set Y to be a quadratic residue, no matter what people try to communicate to me, I get nothing. Okay, so why would I do that? Yeah, but it's a curious property of the Goldwasser-Mercalli system. One could try to kind of use it in other places. For example, here. Okay. So let's try. Good. So here is a proof system. Happens to be for quadratic non-residues. P and V, they both have N and Y. I said use randomness. Let's use randomness. Okay. So the verifier takes R randomly from Z and star. Takes a bit B randomly. Yeah. Random. So he says, look, here it is, R squared times Y to the B. To the program. Which, by the way, is a Goldwasser-Mercalli saxophonist. Yeah. What does the prover do? The prover has unbounded computational power, and his job is to guess what B is. Right? So he sends back B prime, yes, some bit B prime, and the verifier says if B prime equals B, accept, else reject. Yes, that's a protocol. So the real prover, right, would try to find the B. First of all, we are in a setting where the claim that the prover is trying to prove is that Y is a quadratic non-residue. Yes. So if it's not a quadratic non-residue, if it's a residue, he would say, you know what? It's a residue. I'm not going to try to prove a false statement. So we are concerned about the case when incompleteness, for example, we're concerned about X in F. In other words, Y is a non-residue. So if Y is a non-residue, what happens here? Right? We are in the real Goldwasser-Mercalli setting, where Y is a non-residue. So the prover can, he has a factorization or he has unbounded computational power, he can tell what is what. Right? So these, this is the N star. Right? If B is 0, this guy will be this message, call it C, will live here. And if B is 1, well, B is 1. Yes? So C is either a square or not a square. Yes, that's my point. My drawing, well, it's a long story. Okay, all right. Yeah, that's what. So the prover can tell. So this is completeness. Yes, completeness says, yeah, that's good. Soundness is what? Soundness is where Y is not a non-residue. In other words, it is a residue. Maran. In that case, C, as we argued, is a random square no matter what B is. So C completely hides B. So the best that a cheating prover can do, right? The prover is trying to cheat. He's trying to guess what B is to convince the verifier to accept, whereas C shouldn't be. The best the prover can do is to guess randomly. So the probability that the verifier accepts is at most a half. Is a half, really. So Q and R, completeness. Yes. So if Y is not a quadratic residue mod n, so this is the guess case, true theorem case, then out V and in Y is always 1 or accept. No probabilities, always, the prover can always convince the verifier to accept. 2 soundness says if y is in QRN, this is a no case, and y, the probability that the verifier accepts, this is actually the bad case, he shouldn't be accepting. So now I want to say that the probability that this happens is at most something, turns out to be high. What is the probability over here? And this is no matter what the prover does. Yes, what can the prover do? The prover can do whatever they want using the first message, and they can decide to send a bit. Yes, that's all the prover can do. The point is that no matter what the bit set, the prover, no matter which bit the prover sends, the probability that he agrees with B is high. What is the probability over here? Well, no, tell me. It has to be some probability space
Or random bits of the verifier.
of the verifier. That's it. Yes. Not the prover, because the prover can do whatever they want, really, and it could be deterministic and arbitrarily bad. Yes. So I'm not gonna count on the prover tossing random coins. Not gonna happen. Good. So that's what it is. Those are the two properties that the protocol satisfies, and that tells us how to define the complexity class NP, which is a generalization of NP. Feeling extraordinarily lazy today. Let's see. IP. Okay. Is an IP. If there is a probabilistic polynomial time, do have color shows. Probabilistic polynomial time. That's one thing we changed from IP. Such that I'm gonna sort of take the operational interpretation of NP. I'm going to talk about provers and verifiers rather than strings. Completeness says unbounded potentially prover P such that for every instance in the language, the verifier accepts. This could also be probabilistic, right? So the verifier doesn't have to accept it probability 1. It could be probability 0.99. But you know what? I can achieve always probability 1, so let me actually, I can achieve it, why not? And this is actually a theorem. That any IP, any language in IP has a protocol where the completeness error is 0. In other words, the verifier always accepts truth. So that's why I'm going to keep it this way. And this, I'm going to say, well, let's actually write something. Yeah. Out sub V of P star V on equal X, the probability that it's 1 is at most some number S. S is a soundness L. Here it's a half. Anything bounded away from 1, bounded below 1 is good, because you can repeat and amplify. The probability here is over the coins of the verifier. This is a definition of it. Good. And so what we just showed is that Q and R is in fact an F. Okay, so, but that's not what I wanted to do. I wanted to actually show an interruptive proof for quadratic residuosity, not non-residuosity, where the true theorems are in fact the squares, not the non-squares. And you can't flip the two. You can't use the same proof system for quadratic residuosity because, the completeness and soundness conditions, they are asymmetrical. One only works for true theorems, the other one only works for false theorems. So you can't use the same. Yeah, it doesn't even make syntactic sense. How would you prove residuosity? 1 second. Yeah, okay, go ahead.
It's like, I've seen graph non-isomorphism, and it's like similar to this. So
Graph non-isomorphism is similar to what?
that's what I'm going to propose.
Okay, good, all right.
So you pick a random number and you square it,
Uh-huh.
and you pick another one and multiply it with the y, and then you say.
One sec. Let me write it down, otherwise I'm gonna get confused. Okay, so there's a prover, there's a verifier. Yes? There's n and y. You're saying the prover picks a random number r, squares it. Right? So send r squared to the verifier. Or did you mean the other way around?
Yeah, so. I think
So your protocol for graph non-isomorphism, the one you're thinking about,
Yeah.
I'm guessing, will work very similar to the protocol
Yeah.
for non-residuals. This is really the same thing, right? How would you prove that, well, in your language, two graphs are isomorphic, or rather, why is a quadratic residue? It's not entirely clear, yeah.
What if we raise the square root
Uh-huh.
to an odd number and the square to an odd number? And then I don't know if this is zero or not.
Okay, let's see. So y is the supposed square, right?
We raise it to a known odd number.
Second,
We raise it to a known odd number.
known odd number. Okay, let's try. Pick k odd, yes. Y to the k. And are you gonna reveal the k to the verifier? Oh, you are. Okay. Okay, fine. Yeah. So, yeah. Okay.
And then also y to the k, the square root of y to the k.
The root of y. Okay. Yes.
And now the verifier checks if these are, like, y to the k is actually y to the k, and whether squaring the other thing is.
Okay. Fair enough. You're neither using introduction nor randomness. So, Alex. Well, is it even an NP proof? One can think about it, and perhaps if k is relatively prime to phi of n, you can put something. Yeah.
then you know the square root of y, right?
Then you know the square root of y. Why?
Because you can take square root of y.
Kth roots? You can't take kth roots, mod n. That's the RSA problem. Yes? Okay, good. So we'll come back to this in a second. We can neither using randomness nor introduction. I claim they cannot possibly work as a zero knowledge interactive proof. So clearly this problem is in NP, so I can send you something and you will, I can get completeness and soundness.
Oh,
Yes.
like verifier picks a random number, squares it, multiplies it by y,
Yes.
and then gives it to the prover.
Always multiplies by y?
Or maybe he tosses a coin and decides whether to multiply by y or not.
Yes.
And then gives it to the verifier, and the verifier.
Prover and the prover.
And then the prover takes the square root and gives it back. And
Okay, but that won't be, okay, so that's a protocol, but it won't be zero knowledge, yes? So the point is, verifier says, here's r squared times y to the b, yes? And the prover says, here is the square root of r squared times y to the b, yes? And you square this and check if you got this right. If y is a square, then this is always a square, no matter what b is. Yes, so we can always take the square root. If not, half the time you'll fail. But the point is that from this alone, I can actually find the square root of y. Right? The verifier can find the square root of y with probability half. Yes, correctly, right? Yeah. Probability half b is 1. So I'm going to get square root of r squared times y, which is r times square root of y. I know r, the verifier knows r, divided by r, I get the square root of y. Yeah, so you're right. This does use, you guys are very clever. This does use randomness and interaction, but it reveals the yes, what? Yes.
In the top configuration, you actually know square root of y to the k, right?
So here, yeah.
Yeah.
What was the comment?
So you know the square root of y to the k.
Yes.
So then is it knowledge?
Ah, okay. Now we're getting into interesting things. What do you think?
I think it is. Like
Okay, there you go. Right? I mean, it is knowledge. But what is knowledge? Okay. I mean, yeah, intuitively it's clear to you and me that there's something funny going on here. Yeah. I mean, his protocol is revealing knowledge. But what is knowledge? Okay. So let's try to sort of define it. Okay. And we won't define knowledge, it's too complicated. We will define lack of knowledge, or rather zero knowledge. Yes, that's what we'll end up defining. So let me ask you the following question. So what is knowledge? Knowledge is money, yes? I mean, everything is money. Therefore, knowledge is money, yes? What do I mean by that? Well, let's play a game, okay? So I say there are two numbers, 11 and 12, okay? Yeah, you know 11 and 12, I know 11 and 12, yeah? And I tell you, you know what? Here is the product of 11 and 12. What is it, 132? Yes, 132, yeah? I'll give you the product of 11 and 12 if you give me $1. Okay, that's the game we're going to do. Will you give me $1? I claim you shouldn't. Okay. Why? Because this is something that you could have done yourself. Yes, in the comfort of your dorm room, you could have computed 11 times 12. You would get the answer. Why would you give me $1 for it? Doesn't make any sense. Okay. So the point is, things you can compute by yourself in polynomial time reveal no knowledge to you. It is not useful to you. You won't pay money for it. Therefore, it reveals no knowledge. Here's another experiment. I toss 50 random coins. Okay, so this is a new startup idea I have. Okay, random coins. Might work. And I say every random coin costs $1. I sell you 50 random coins. Say, I'll give it to you if you give me $50. Will you give it to me? Well, it depends. Like, you can argue one way or the other. But randomness is a free commodity. Okay, I mean, randomness is something that I can toss coins. We are in a world where you have perfect coins, and everyone has at least a penny. Okay, so you can keep tossing, you get 50 random coins. So you shouldn't be giving me $50. Yes, it doesn't make any sense. So randomness is for free. So if I send you random coins, you can toss random coins by yourself, so you won't pay money for it. Therefore, anything that you can do using random coins and polynomial time, which by the way is probabilistic polynomial time, you won't pay money for it. Everything else, well, for example, now I say, you know what? It's not 132. It's a large, 100-digit number. Okay, so you and I know it, and I say it's a product of two primes. I'll send you the factorization. Can you give me $50? You might. If this 100-digit number is a public key of, the Bitcoin wallet, which has a lot of money, you will give me $50. Yes. So that is worth money. It's worth money because you couldn't have done it yourself in probabilistic polynomial. Right? So, what is an interaction? An interaction is said to convey zero knowledge if whatever you see in the course of the interaction you could have come up with it. Yeah, and we'll have to say what that means exactly in probabilistic polynomial time, knowing only the statement, which is x, and the fact that the statement is true. Yes. So this is not something I'm trying to hide. The fact that the statement is true, that the truth of the statement is for free. I mean, I give it to you, right? So if you can come up with the transcript of the instruction, what does it mean, the transcript of the instruction? It's a random variable, right? It's a random variable. If you can come up with the same random variable, you can sample from the same random variable in probabilistic polynomial time, knowing only the statement and the fact that the statement is true, then this instruction will be zero knowledge. So let's write it down. Make sure we're on the same. So, an interactive protocol, PD, is, I'm going to leave some space here, zero knowledge. If there exists an algorithm S, now I have to define something else. Yeah? So I have to define what does the verifier see during the course of this interaction. Okay, so I'll call this the view of the verifier in the course of interaction, with X as the common input. So this is, what should it be? It should be the transcript of the interaction, right? Which in this example is C and B prime. Yes. Whatever I see from the prover. And what? What else do I see in the course? What else does the verifier see in the course of this interaction? Certainly the transcript. The coins that it tosses. It's not something that I see externally, but I do see it. I mean, yeah. So I have to include that. Yeah, so this is the view of this is the entirety of what the verifier sees in the course of this interaction. What I want to say, so this is the definition of zero knowledge. This protocol is zero knowledge. If there is a way, instead of interacting with the prover, if there is a way for the verifier to run an algorithm that generates a distribution that is exactly the same as the view. Interacting. So I don't have to go out and interact with this P guy. I could have kind of, sat in my room, yeah, and generated this view myself, knowing X and the fact that X is true. So this I'm not trying to hide from the whole point of the interaction was to tell this bit of information to the I'm not trying to hide it. So if there is a probabilistic polynomial time algorithm S, I'll call this the simulator, such that for every X in the language, yes, so is a verifier that is bad. Okay, so it's a verifier that is trying to sort of extract information. So, extract information about what? About a proof of an X in the language. So this only makes sense when X is actually a true theorem. Yeah? This is a random variable because this is a probabilistic polynomial time algorithm. It gets X, yes? And we're only quantifying over X is in the language. So S also knows that X is in the language. And it runs on X, yes? It generates some distribution. And this has to be the same random variable as the view of the verifier on this interaction. And then I call this zero knowledge. Yes? Yeah, so this says, the simulator gets polynomial time and coins for free, and it manages to generate the exact sort of view that the verifier sees, and therefore there is no knowledge transfer. You know, therefore for this interaction, right? If I told you, look, I'm going to sell you a random interaction in this protocol, coins together with transcript for $50, you would say no. Why? Because you could have generated it yourself. Answer. Question? No.
No, it just
Good. Okay. Okay. This guy, yes,
yeah.
is not zero knowledge. Why? Because what does it take for someone to simulate this? From the view of the verifier, I can extract the square root of y half the time. That is not something that the probabilistic polynomial time S can do. Yes, so therefore this is not zero knowledge according to the definition, if quadratic reciprocity is a hard problem. Yes, I mean, so in general it's not clear how to design a simulator. Another way to say it is that to prove that a protocol is zero knowledge, the onus is on you to design, to show a simulator. If you design the protocol, you have to show a simulator which, then you can claim that this protocol is zero knowledge and I'll believe you. Yes? So now let's see, again, this guy, yes? What is a simulator? Yes, so you design the protocol, the onus is on you to come up with a simulator. Yeah. I don't see it. It's quite unclear. I mean, in fact, there was a reason why this cannot be zero knowledge. How about this guy on the other hand? Yeah, the onus is on me. I have to show you a simulator. Yes. How would I simulate? How would I come up with an algorithm that generates the view of B in this interaction? What does the view of B contain? I'm just going to abbreviate it this way. Is the coins, which is R comma B, right? And the transcript of the interaction, which is C, and well, B prime when X is in the language and the prover is the real prover, B prime is equal to B, so, which is basically C. You can write it as C comma B, but this is the coins and this is the transcript. Yeah, this is what I have to generate. This joint distribution is what I have to generate. How would I do it? Well, I can first take B, right? Random bits, which is exactly the way it's supposed to be. I can pick a random R, square it, and compute C as R squared times Y2. It's precisely exactly the same. So in other words, what I'm saying is, forget that, the simulator has a power to generate the entire transcript without having to wait for the verifier in the PC's definition. So then I can sort of, pick the second message and then generate the first message. And this is precisely exactly the same as what the verifier sees. Yes?
How does this handle the case where B does not do what?
This is called honest verifier zero knowledge, right? Which means the verifier has a protocol, it does exactly what the protocol tells it to do. If it asks to toss coins, it will toss coins. If it says to compute a message, it will compute a message. But then you say, well, so what is it trying to do? What it's trying to do is it's trying to look at the entire interaction, what it gets from the prover, and then later he goes back and he thinks about it in the comfort of his room and says, well, can I extract something out of it? Okay, so this guy, yes, even if the verifier is honest, he can go back to his room and he can say, look, let me divide this by the R and try to get square root y. And this is not even honest verifier zero knowledge. Yes. But you're right that But the world is malicious, yes? I mean, so at least in the soundness definition, I allow the prover to do whatever they want. So of course I have to let the verifier do whatever they want. Yes? Assuming you guys wrote this down. Or there's a video. So. Is zero knowledge? Yes. Zero knowledge or general zero knowledge or malicious verified zero knowledge. I'm just going to call it zero knowledge. Yes. If what? What happens? What should I change here? I am no longer trying to simulate the view of V, the honest verifier. I'm trying to simulate the view of any verifier. If for every PPT verifier V star stands for a potentially malicious verifier. There is a simulator which can generate the view of V star on this interaction. So now I'm not trying to generate the view of the V that I designed, the honest verifier, but rather any V star. Okay. So, this is sometimes too constrained, asking the simulator to produce exactly the same distribution, is too constrained. We know that exact equality of distribution does not matter, all that matters is that these two distributions are computationally indistinguishable. I mean, for practical purposes, it's really the only thing that matters. So then I would say, for every PPT distinguisher D, the probability that D distinguishes between these two guys is negligible. I'm not going to write the whole kind of thing, right? I mean, I'm just going to say this is indistinguishable by D. This is a shortcut to the whole probability statement. Yes, this says the probability that D given S of X, the random variable outputs 1, is close, negligibly close to the probability that D outputs 1 on input, the real view. Okay, malicious verifier. So this, I don't care what the verifier does. Go crazy. Okay, so now you can ask, is this protocol malicious verifier zero knowledge? Why not, actually, intuitively? I mean, to show that it's not zero knowledge, you have to say that there is no simulator, but intuitively why?
I can use the prover to decrypt bits I don't know.
Right. Does this make sense? What's going on? Right. So here, the real verifier generates an encryption of a bit that he knows. Therefore, what the prover sends back is zero information, zero knowledge. Yes. But a malicious verifier could pluck out sort of encryptions from the sky, right? He could send it to the prover and get the prover to decrypt it. Right? So, yeah, that's the intuition. So, not gonna count. Yeah, this makes sense? No? So, the question to ask is, how are you going to simulate this interaction with a malicious verifier V star? Okay? So V star, here is a V star. V star just generates a random number in Zn star, say with Jacobi symbol 1, whatever. It gives it to the verifier, it gives it to the prover. The prover is supposed to tell whether this is a quadratic residue or non-residue. That's what D means here. That's the interaction. Yes? Now you want to simulate the verifier's view in this interaction. And let's say for a moment that V did not kind of generate this random number in its head. It actually took a number, 13, okay? 13. It wants to find if 13 is a square mod n or not. Okay, so it says 13 here, right? And the prover faithfully says, I'll tell you, I'll find it out, and I'll tell you the answer. How do you simulate this? You can't, I mean, at least this protocol. In general, you can try to show a simulator, yes? And if you can't, it's not yet zero knowledge. Again, the intuition is this. You can pluck out numbers, 13 from the sky, you can get a decryption of 13. All right, so we have to fix it. We have to fix it, and we will actually fix it in its generality, right? But let me show a simple protocol that is actually malicious verified zero knowledge. Yes, I have to show you some positive example. So that is QR. I'm sure that this is actually, I'll show not just an honest verified zero knowledge protocol for it, but also a zero knowledge protocol. So here's the protocol. Yeah, okay, so 1, 2, and here is 3, yes? So an interactive, I'm not going to write down everything in the same place. The interactive protocol is a zero knowledge interactive protocol if it is complete, sound, and zero knowledge, 1, 2, and 3. Completeness refers to the setting where the prover and verifier are honest, the normal mode of operation. Soundness refers to the setting where the prover is dishonest but the verifier is honest. Zero knowledge refers to the prover is honest and the verifier is dishonest. Awesome.
Can I try to guess it or?
Sure, go ahead. The second time is a charm. Yes.
So you pick a random square and you multiply it by y, and
You is who? The prover.
the verifier.
The verifier.
And the verifier picks a random non-residue that has a Jacobi single one and sends both to the prover, and prover tells which one is which.
1 second. All right, wait. Write it down. So again, verifier, the prover. The prover picks a random square, right? Times y.
Yes.
Yes. And he also picks a random number with
non-residue that has Jacobi single one.
numbers to do with Jacobi symbol. So let me say, so C prime is number Z in Jacobi 1 minus quadratic residue. Yes? Good. Now what?
Now the verifier says, like,
The prover says.
the prover says which one was which. So it gives a random permutation of them.
The prover says. Okay, so Y is a random.
It should run into the same problem as the other one.
As
the QNR.
this one. Yeah, that's the intuition. But
It's not just intuition. If you have a thing and you want to decide, you pick them at random and send it along with it.
oh, what? Sorry.
Again, 13 and
13 and
random.
15. Yes.
Yeah.
Okay. Well, I don't. So you know what? Don't listen to that guy. Okay. Just do not listen to that guy. Try to find a simulator. Good luck. Don't listen to me either. I mean, the best way to kind of do this is just hit it. You know why? All right. So should I even tell them the protocol? You know what? I'm very conflicted now. Okay, I'll tell. Arson, close your ears and.
And your eyes.
Oh, it's eyes. Yeah. Okay, so. So here's the protocol. It's an instance of what I'll call the commit, challenge, and response protocol. So there are three messages. The prover is the one that initiates the interaction at this point. So he sends a random square. The verifier sends a bit. What? B. Randomly chosen from 0 to B. and the input is n and y. Yeah, this is. So far, no one has even touched y. Yeah. So the prover says the following. This is a very shocking question, which I like a lot, but it's very hard to reproduce. So let me see. The prover is not going to send the square root of y to the verifier. But he says, I could have produced the square root of y if I wanted to. Okay. But I'm not going to send you the square root of y. You have to bring Shafi into the into the role to say this. Okay, so what does that mean? He says, look, if b is 0, so this is a notation. Well, b is 0, you send r, the prover sends back r, which is basically the square root of what I sent, which has nothing to do with y. Okay. Call it z. If b is 1, the prover sends, well, let me just say square root of z here. Yeah. Square root of z times y. Okay. So both of these don't happen at the same time. I mean, this notation is a bit, well. Yes. And what does the verifier do? The verifier squares this number and checks if it is equal to z times y to the b. Yes, so call this w. The verifier checks if w squared is equal to z times y to the b. So, let's write it down. So either square root z or square root of z times y. That's what the prover says. So the prover is not sending the square root of y, right? But if the prover is able to answer both challenges, b equals 0 and b equals 1, then he must have known both the square root of z and the square root of z times y. In other words, square root of y, dividing the. So the prover is not sending the square root of y, but she is saying, I could have sent the square root of y if I wanted to. Right? If I wanted to, meaning if I could have responded to both the 0 and the 1 challenge, I knew square root of y and I could have sent it, but I'm not going to send it to you in any one instruction. That's the point. Yes, so you have to show this is complete, sound, and zero knowledge, in malicious zero knowledge. Let me argue completeness, soundness, and honest verified zero knowledge. But we'll postpone that. All right, completeness. You see. Yeah. Completeness. In the normal mode of operation, right? If the messages are exactly the way they are, then the verifier will always accept. If y is a square. Soundness. This is the setting where the prover is corrupt. It can decide to send whatever it wants in the first message, and given a b, it can decide to do whatever it wants to make the verifier accept. Okay, so let's fix a prover message z, right? And suppose the prover can now make the verifier accept given the verifier challenge 0 and the verifier challenge 1. Right? Yeah. So that, in other words, he always makes the verifier accept. Then he computes that he has a square root of z and he has a square root of z times y. Dividing the two, he has a square root of y. In other words, y is a quadratic residue. But for every ny, such that y is not a quadratic residue. That's contradicting the assumption that y is not a quadratic residue. Yeah. So in other words, for every quadratic non-residue, the prover can answer correctly for either the challenge 0 or the challenge 1. Right? no matter how he chose the first message, but not both. So the probability that out sub b without equals accept is at most half. For any prover of p star, the probability that you can make the verifier accept is at most half. In fact, you can see that this is tight. There is a prover that can make the verifier accept with probability exactly half. Yeah? So that's that sounds. Zero knowledge. Well, let's just do honest verifier zero knowledge. Should we do it? You know what? Go back and think about it. Arsen, you should think about. You have two protocols to think about. Okay. We'll do this in the next class. Okay.